Okay, so this is complex numbers and matrices question, 2011. It's question 3, and it'll be on paper 1. The A part and the B part are fairly straightforward, so I'm going to try and get through them as quickly as I can. Part A, very straightforward question. 1 plus 2i all over 2 minus I. You're asked to express it in the form a plus bi. You'll multiply above and below by the conjugate. When you do that, that's a 2 there. You'll come out with that. I squared is minus 1 if you remember, so that's really a minus 2, and this is really a plus 1 here. When you tidy all of that up, you'll have 5i over 5, leaving you with I. If you leave it with I, you will be docked 3 marks. You must put it in the form a plus bi. On to the B part 1. Find two complex numbers such that you've got a plus bi all squared is equal to minus 3. The way you're going to go with this question is you're going to square out the you're going to square out the left hand side and basically equate coefficients and solve for a and b. So you'll end up with a squared minus b squared plus 2abi minus 3 plus 4i. Reals with reals, imaginaries with imaginaries, so you'll have a squared minus b squared is equal to 3, and you'll have 2ab is equal to 4, ab is equal to 2, and it's up to yourselves then what you decide to do. I'm going to solve for b, so b is equal to 2 over a. You're going to take that, you're going to square it out, and it's going to go in there. Going to multiply across by a squared, so you'll end up with a to the 4 and you'll have to solve that out. Now that's really just a quadratic. There are different ways to sort of tackle that. I'm just going to come up here, block this off and come up. What you could do is you could let x equal to a squared, because a to the 4 really means a squared to be squared plus 3a squared minus 4 equals to 0. If you let x equal to a squared, you'll have x squared plus 3x minus 4 equals to 0. You'll be able to solve that. So x will equal to 1, or x will equal to minus 4. But we know that x is equal to a squared, so a squared is equal to 1, or a squared is equal to minus 4. So that means a is equal to plus or minus 1, and we reject the a squared equals to minus 4. There's no number squared that can equal to minus 4. So now we have our two values of a. We can go ahead and we can solve for our values of b without dwelling on it too much. If a is equal to 1, b is equal to 2. If a is equal to minus 1, then b is equal to minus 2. Now of course this little substitution, this method here, it's not absolutely necessary. If you can see that yourselves and you don't need to use the substitution, that's perfectly acceptable. You won't be docked or penalised in any way, shape or form for it. Okay, moving on, the next part. Sorry, on that, just before I move on, just to make sure that you answer the question the way that you've been asked, so this is just a continuation of part 1. You are asked to find the two complex numbers a plus bi, so you do have to say 1 plus 2i is one complex number and minus 1 minus 2i is the other. And what's also worth noticing is that another way of combining the solution is that. Now, if you do this or if you do this, you'll still get full marks, but you need to make sure that you do say the solution is equal to, give the answers in the form a plus bi. On to part 2. It says hence solve. Now the word hence is important because that's going to tell you that maybe there will be something of relevance from your part 1. You've got a quadratic, it's x squared plus x plus 1 minus I, and I'm going to put the 1 minus I in brackets. Essentially that's just a quadratic equation. A is equal to 1, b is equal to 1, and c is equal to 1 minus I. To solve quadratics, I'll use the minus b formula, so x is equal to minus, we won't bother writing out the formula, so minus b, so minus 1 plus or minus the square root b squared, so 1 squared minus 4 times 1 times c, which is 1 minus I, all over 2a, which is there. I'm going to tidy that up a little bit. Minus 1 plus or minus, it'll be the square root of 3 minus 3 plus 4i all over 2. And what you need to spot here is the root of 3 plus 4i. I just want to go, as a little aside, go back to question 1, or part 1. A plus bi squared is equal to minus 3 plus 4i. Well, if I root both sides, I get a plus bi is equal to the square root. So if I already know what the square root of minus 3 plus 4i is, well then I can exchange it for part 2 of the question. And I know that my answer for a plus bi is plus or minus 1 plus 2i. So a little exchange is going to take place. X is going to equal to minus 1 plus or minus 1 plus 2i all over 2. You can continue to tidy that up. Sorry, you're going to split it now, so x is equal to minus 1, well it'll be plus 1 plus 2i over 2, or a little bit sloppy there, x is equal to minus 1, it'll be minus 1 again, minus 2i. Make sure you watch your signs there, all over 2. So your two answers, x equals I, or x equals minus 1 minus I. And I'd be inclined there to say that that's x is equal to 0 plus I. Just give your answer in the form that they ask. Okay, so that's the A and the B part. Fairly straightforward stuff, and you'd have seen it before in other exam questions. On now to the C part. There's a lot going on. It certainly looks like a complicated question, so you need to make sure that you read each and every part, that you take your time, and that you have a little think about what your plan is going to be before you launch off into the question. So A and B, they are both 2 by 2 matrices. We're not told what A and B are. Where A has an inverse, we're asked to show that. So this is just a proof of one of the properties of matrices. Prove that, or show that A inverse B times A all to the power of n is equal to A inverse B to the n A. So that's what we're trying to show. So to answer it, we'll take the left hand side and we'll have a look at what it actually means. Well, what it means is A inverse B A multiplied by itself n times. And the way we'll just show that is just with dot dot dot. We'll show that it continues on. Up as far as whatever value of n we had been given. And then what you need to do is you need to just highlight these areas here. And what you can see is that beside you've got A multiplied by A inverse. And whenever you multiply a matrix by its inverse, you get the identity matrix. So what you'll end up with then is A inverse B times the identity matrix times B times the identity matrix B times the identity matrix, and that process will continue on till you get a BA at the end, because that A inverse there that I've just underlined, well, there will be an A there. You don't need to get too fussy. It's not like somebody you're talking through for the examiner. You just need to display your work. Obviously, any matrix B multiplied by the identity matrix itself is just going to be B. So A inverse, it'll be B times B times B, BA. What you'll be left with is A inverse, well, B by B is B squared, B by B by B is cubed. Depending on how many times you've multiplied your original, which is n, you'll end up with B to the n, A, and that's part 1 done. Part 2 of the question. This time you're given two matrices. You're given P and you're given M, and you're asked to do a little bit of evaluating. So probably a good thing to do would maybe have a think forward. I'm certainly going to have to get P inverse, so even before you begin working with the actual question, that might be an idea. So P is the matrix 3, 1, 5, 2. That means that P inverse is given by, and there's a little formula, it's 1 over AD minus BC. And if you remember the AD BC, well, that kind of tells you what to do. Remember, this is A, B, C, and D. So what I always remember is I swap the A and the D, and I change the signs of the B and the C. And 1 over AD BC is just 1 itself. Of course, that scalar 1 multiplies in, so now I know that P inverse and now you can move forward with the question. So I'm just going to change page. So what you're actually asked to work with, first of all, is evaluate P inverse M P. So we know that P inverse is 2 minus 1 minus 5, 3. M, we're given in the question, is minus 5, 3 minus 10, 6. And then P itself we're also given. Now, just resist the urge to move the P to give you a P by a P inverse and then cancel it out, etc. Matrix multiplication is not commutative, so you can't just move it around or switch it around whatever way you want. What I find when you're doing these, if you ever have three matrices or matrix to multiply by each other, I often find it's easiest if you multiply the last two and work back. We're usually used to working from left to right. Find if you do this, you work from right to left. I don't know, it just seems to work out that little bit easier for us. So I'm going to multiply these ones. I'm not going to do it for everything, but I'm going to show you how to multiply these two, and then you can apply it to everything that you do. So you've got a row, a column. It's a 2 by 2 and a 2 by 2. If you remember, these numbers being the same tell me that I can multiply them. These numbers here tell me what the resultant matrix is going to be. If you remember in class, what I advised you to do was draw a big cross, big matrix, and write all of your calculations into it, and then you can tidy it up. So I've got row and column highlighted there, so it's going to be minus 5 by 3 plus 3 by 5, and then I'll multiply the same row, the minus 5 and the 3, by the next column over, which is in red now. So I'll have minus 5 by 1 plus 3 by 2. Once I've got that done, I'll move down to the green. I'll write this in green, so it's going to be minus 10 by 3 plus 6 by 5. And then I'll go again, it'll be the sign of it will be green by red, so it'll be minus 10 by 1, 6 by 2. So when you've got all of that, remember this matrix of here still drops down, so you're going to end up with something along these lines, or exactly this hopefully. Minus 1, minus 5, 3, that's your matrix brought down, that's P inverse. And you'll then have to multiply that by the matrix 0, 1, 0, 2. Now I'm not going to multiply that out, you can apply the same technique. When you do that, you'll end up with 0, 0, 0, 1. I'd advise you to multiply out the matrices. Don't take matrix multiplication for granted. It's not difficult, it's not awkward, it's a little bit tedious, but people make mistakes regularly in it. Next thing you are asked to evaluate is P inverse MP all to the power of n. Now again, this is one of the properties that you have seen, so hopefully you know that on the one hand this is not all that relevant, but on the one to this particular question, and you saw that earlier on, and that might be your first instinct, but what this is actually saying to you is there's also a property of matrices, and if you have a matrix and it's a diagonal matrix, and you have the matrix P inverse MP, and that's equal to a matrix, we'll say just a 2 by 2 matrix just to make things nice and handy. I'm going to put in an A and a B. Well, if I put that all to the power of n, that means I'm putting this all to the power of n. And then there's the property says that I can say, well, that's A to the n, and that I can just raise the diagonal to whatever power I'm looking for, and I'll get my answer. So if we apply that logic to what we're dealing with, the matrix that we actually have is 0, 0, 0, 1. It's a diagonal matrix, and we know it's a diagonal matrix because we've got this here, and all other values are 0. So what that really means is 0 to the n, 0, 0, 1 to the n. So you just have to say to yourself, well, I know you've no value for n. 0 to any number, well, that's still going to be 0. I know this is getting a little bit tight here now. 0 stays the same, 0. 1 to the power of any number, it'll still be 1. So you've evaluated it. Okay, moving on. Last part of the question. Again, you've got a hence or otherwise, so you're presuming that the stuff that you've used is going to be relevant. Hence or otherwise show that m to the n is actually equal to m. So, what are you going to do? Well, part of it is trying to decide, you've got two things. Now, one of the things I wrote down earlier on for you, just a moment ago, I'll just put it over on the side, is that if you had P inverse P all to the n, that was equal to P inverse n P. So, looking at that fact, it looks like we're going to try and do something with this. Now we know that P inverse m to the n P, we've just worked that out. We know that that matrix is 0, 0, 0, 1. And what that sort of tells us is, if I can isolate m to the n, well then I can compare it against the value for m, which is given to me in the question anyway. So the only thing that you're trying to find here is m to the n. So to do that, I must pre-multiply here by p. If I pre-multiply, I must pre-multiply. If I post-multiply, I must post-multiply. So you'll get m to the n is equal to, well, my value for p is 3152. You'll multiply that by 0, 0, 0, 1, and you'll multiply that then by P inverse, which you calculated much earlier on, 2 minus 1 minus 5, 3. Again, my advice to you would be to multiply these two out first. When you do that, you should get 0, 0 minus 5, 3. Of course, the other matrix, 3, 1, 5, 2 will drop down. When you multiply the two of those, minus 5, 3, minus 10, 6. So mn is equal to that, and if you have a look back at the question, that's equal to m. So your job is done. That's it.